Today I will present my this titled Data-Driven Approach to Warehouse Storage Location Optimization Using Association Rule, Meaning, and K-means Clustering comparison with traditional ABC analysis. This study focuses on warehouse storage location assessment. More specifically, it explores whether association rule, meaning, and K-means clustering can improve storage decisions compared with the traditional ABC method. This research starts from a potential warehouse problem. Order picking test time and product locations directly affect picking efficiency. Traditional ABC analysis is commonly used in warehouse, but it mainly classifies products based on frequency or importance. It does not fully consider whether products are frequently packed together. Therefore, this study proposes a data-driven method. First, a priori association rule, meaning is used to discover product concrete patterns. Then, K-means clustering is applied to group products based on association rule behavior. Finally, the proposed cluster-based strange plan is compared with the ABC-based plan through simulation. Warehouse picking efficiency has a direct impact on operational cost and service performance. In many warehouses, products are arranged using traditional ABC analysis. However, ABC analysis is a one-dimensional method. It usually focuses on product impedance, sales volume, or picking frequency. This creates a limitation because the products that often ordered together may still be started for part. For example, a high-frequency product and a lower-frequency complementary product may appear together in many picking bases, but ABC may place them in different warehouse zones. This can increase picker travel distance and reduce operational efficiency. Therefore, the main problem of this study is that traditional ABC classification may ignore product concrete relationships in real warehouse order. This study has 5 main objectives. First, it aims to identify product operators using the a priori algorithm. Second, it groups skills based on association rule behavior. Third, it develops a cluster-based storage location assessment plan. Fourth, it compares the proposed plan with the traditional ABC-based storage plan. Finally, it provides potential data-driven framework for warehouse storage optimization. In simple terms, the study follows a clear process: identify relationships, classify products behaviorally, assign storage locations, and evaluate the improvement. Chapter 2 reviews the key features related to this study. The first part discusses warehouse storage location assessment, including randomized storage, declarative storage, and class-based storage. The second part reviews association rule meaning, especially how a priori can identify product activity in traditional data. The third part discusses cluster analysis and K-means clustering, which can group products based on similar behavior. The final part reviews the traditional ABC analysis and its limitations. The main research gap is that provides studies often use the association rules or clustering separately, but fewer studies integrate both methods and compare the results directly with traditional ABC classification. The conceptual framework shows the logic of the study. The process begins with historical order data. Then a priori association rule meaning is applied to discover product relationships. After that, association rule constructed for each product. These features are used as input for K-means behavioral clustering. The clustering results are then compared with the traditional ABC classification. Finally, a storage location simulation is conducted to evaluate whether the cluster-based assessment can reduce picking distance. This framework connects data meaning results with potential warehouse storage decisions. The method consists of 4 main stages. The first stage is data processing, in which the records are removed and order lines are grouped by wave number to form transaction baskets. The second stage is association rule meaning. A priori is applied with minimum support of 0.005, minimum confidence of 0.5, and left greater than 1.0. The third stage is product clustering. Association rule-based product features are constructed, and K-means clustering is used with K equals 4. The first stage is simulation. 2 scenarios are compared. Scenario A is traditional ABC-based storage assessment, and scenario B is the proposed cluster-based assessment. The dataset used in this study is a public warehouse operational dataset. After cleaning, the final analytical dataset contains 122,337 valid order line records. The records are translated into 9,784 with number picking batches involving 208 skills. The data covers approximately 9.4 months of warehouse operations. For proposing, invalid records with non-positive quantity were removed. Then product lines were grouped by wave number, where each wave number represents one picking batch. Finally, product persons were placed into 0 and 1 values. So the a priori algorithm could identify frequent product conditions. The a priori algorithm granted 1003 association rules after applying the select results. One important example is the rule G8ASPE-KUFVRI to 1GT1SB with a left value of 25.56. This means that when G8ASPE and KUFVRI appear together in a picking base, 1GT1SB is also very likely to appear. The high left value shows that this relationship is much stronger than random chance. These rules reveal product concrete patterns that traditional ABC analysis cannot capture. In particular, some relationships cross ABC candidates, meaning that lower frequency products may still be operationally important because the frequency picked with poor products. After association rules were granted, product-level association frequencies were constructed. These frequencies were then used for k-means clustering. The study selected k equals 4, producing for behavioral clusters. Cluster 1 represents accrue high association atoms. Cluster 2 represents dominant high-frequency material atoms. Cluster 3 include moderate frequency associated atoms. Cluster 4 contains low-frequency or relatively independent atoms. The cross comparison with ABC classification shows an important finding. Behavioral clusters do not simply repeat ABC categories. Most Class A products were tested in Cluster 3 rather than Cluster 1, and many Class B and Class C products also appeared in Class 3 and Class 4. This confirms that ABC and behavioral clustering capture different dimensions of product independence or product importance. This is the key result of the study. Two storage assessment scenarios were compared. Scenario A used the traditional ABC-based assessment, while Scenario B used the proposed cluster-based assessment. The simulation was conducted using 10 representative multi-product test orders. The results show that the total picking distance under the ABC-based plan was 18,420. Under the cluster-based plan, the total picking distance was reduced to 14,215. This means the proposed method saved 4,117 distance units, representing a 22.6% simulated picking distance reduction. This result supports the idea that storing behaviorally related products closer together can reduce unnecessary movement and improve picking efficiency. The finding provide both theoretical and potential implications. Theoretically, this study integrates association rule meaning and k-means clustering into one framework for storage location assessment. It also extends the traditional ABC analysis by adding a behavioral product relationship dimension. Particularly, the results suggest that the warehouse manager should not rely on individual product frequency. They should also consider which products are frequently packaged together. The proposed approach does not completely replace ABC analysis. Instead, it complements traditional ABC analysis by adding product affinity information. It can help managers make more informed storage location decisions. This study has several limitations. First, it uses the one public warehouse dataset, so the generalizability should be tested with more warehouse and industries. Second, Euclidean distance is used as a simplified simulation measure, so it does not fully represent real picker movement in warehouse assets. Third, the study is simulation-based, does not include real warehouse deployment. First, only a priori and k-means are tested. Based on these limitations, the study successfully identified 1,003 association rules, granted 4 behavioral clusters, and achieved a 22.6% reduction in simulated picking distance and achieved a 22.6% reduction in simulated picking distance. In conclusion, this research shows that data-driven storage location assessment approach can improve warehouse picking efficiency and provide a useful complement to traditional ABC analysis. Thank you.